Hi, welcome to our next set of notes that we're going to be talking about the algebraic approach. What we've done up to this point is we've taken a look at how to numerically use a table of values to determine what a limit is. We've looked at using the graph to determine what a limit is. So now we're going to start building kind of our toolbox of algebraic techniques for finding limits using things like factoring or rationalizing, just some different techniques, some trig substitutions, some simplifying expressions kind of ideas that are going to help us calculate and find limits algebraically. All right, so we're going to take a look at our first example right here. And in our first example, as we're looking at it here, that what you see is that we're trying to calculate the limit as x approaches a. And so we have different values. We have 0, we have 2 from the right, and we have 10 here. And so what we're going to do is we're first going to find the function value using the equation, and then we're going to find the limit by taking a look at the graph. And our graph right here is a pretty straightforward absolute value. It has a little bit of a transformation in it because we have stuff going on here on the inside, and we have a picture of this. So right now we're just going to use the graph that we have and kind of work our way through it. So the first thing, of course, you're going to do is you're going to calculate the function values. So what we're going to do, and I'm going to kind of pause because in this video we're going to have you prompt and find the values. So the first thing you're going to do is you're going to find f of 0, you're going to find f of 2, and you're going to find f of 10 using the equation. Then what you're going to do is you're going to actually calculate the limit as x approaches 0 of f of x. And I do want you to go ahead and write that in each time, just because I want to be able to see your notation for that you're using correct notation. So we're going to do the limit as x approaches 2 from the right of f of x, and we're going to do the limit as x approaches 10 of f of x. And we're going to use the graph over here to go ahead and answer those questions. So I'm going to pause. I'm going to let you fill in those questions, and then we're going to come back together after you've answered the questions in Edpuzzle. All right, so coming back in, what we've done is we've found each of these values, and a little bit of sneakiness that we had there, you start to say, I can look at the graph very easily and get that this is approaching -2 as x is approaching 0, so we're at that portion of the graph, and plugging in 0, very straightforward, is going to be -2. Plugging in 2, we end up with this -4, and again, we can see down here that as x approaches 2, from the right, so that would be from this direction heading down, we are also heading to the -4, which is there. And then f of 10, plugging in, you get 4. And then you may have been like, well, how am I supposed to see it on the graph when the graph isn't there? So maybe you came over here and you extended this out so that you could see what it is. Or maybe you can start to see kind of the point of this activity that for this function, you're going to notice that each of these are exactly the same. So we got -4 and -4 are 4, and this one is going to be 4. And so the question that we ask ourselves is kind of what the main point of this is. And the point of this discussion and what's nice about the absolute value function that we're looking at is that the absolute value function is a continuous function. And when it's continuous at the value that you're interested in finding the limit for, your limit as x approaches a, how can we actually find it analytically? We're basically just going to use direct substitution. And so basically what that says is if f is continuous at x equal to a, then the limit as x approaches a of f of x is exactly going to be equal to f of a. And this is a very, very powerful conclusion that we have, which means that as provided that you have a really, 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 really nice function, and by that we mean a continuous function, we can calculate the limit where the graph is headed, the intended y values by simply plugging in. Now, hopefully you'll notice that that isn't always true. That is only true if we are continuous at x equal to a. Now, right now, we're not looking at the calculus definition of continuity, which is going to come later in this section. What we're looking at is kind of using our pre-calculus knowledge to determine when something is continuous. We have a lot of parent graphs that we are familiar with, and we're also familiar with finding things like domain and kind of picturing what the functions are looking at. So for example, when I'm looking at this function right here, which is simply a quadratic, you should in your mind be able to picture that a quadratic, a parabola, is going to be continuous everywhere. The different types of functions that we have in this activity, we have rational functions here and here. So you may want to think about where rational functions are discontinuous and where they are continuous. We have a trig function here. Let's scroll up, and we have a trig function right here as well. Here we have a nice log function that we did at the kind of first semester last year. Here we have a radical in a fraction, and we did a lot of work in semester 1 in pre-calc on finding the domain of functions like this. And so we have this one as well. So the first thing that I'm going to do before you even go to find the limit, what I'm going to want you to do is step number 1, and then we're going to ask you to answer this question as you go, is I want you to state the domain of f of x for each of these functions that's there. So think about your pre-calc skills and come up with your domain. And then think about, based on what you know about those types of common functions from pre-cal, what continuity do you have at x equal to a? Is the function continuous at x equal to a? All right, so we're going to do that, and we're going to come back together, answer the questions that come up in Edpuzzle, and then we will move on to actually finding the limits. All right, coming back in, so most of you are fairly good on things like quadratics, which of course their domain is all real numbers, and they are continuous everywhere. So there's no holes, no gaps, things that we had looked at in Algebra 2 and in pre-calculus. No vertical asymptotes, no holes, no missing values. So you can draw it with your pencil from beginning to the end. Again, this is a layman's term, pre-calc definition of continuity, but we're using what we know about parent functions to help us out here. Our rational functions, we know that rational functions are continuous everywhere except for what causes division by 0. They're continuous on their entire domain. And the domain, of course, doesn't include positive 3/2 here. Our nice little rational function over here, again. Now, I notice I did a factoring for this one. And now notation-wise, this has a little bit to do with what we call linkage in calculus. That when we are doing this notation, yes, I was factoring the bottom because I know the denominator cannot be 0. That's how I find my domain. And if you are going to do this within the work of this problem and put in equals right here, you have not performed the limit yet. And since I have not performed the limit yet, I have to bring this along and write this down. Now, what I could do for this problem is come over to the side and simply do x squared plus 2x minus 3 cannot equal 0, and then factor there, x plus 3, x minus 1 cannot equal 0. If I do it over on the side like that, then what I basically can do is kind of preemptively not have problems with what we call that linkage error, because you're doing this as quote unquote scratch work over on the side. So if I do that as scratch work on the side, it's not embedded within the problem that I'm trying to do, then I don't even really need to write the line that I have as the second line right here, that I can kind of skip that. But you don't want to simply factor the bottom and not put this limit there. Now I'm going to leave this in for work for this because there's going to be a reason for this a little bit later, but I just wanted to kind of talk about that a little bit to be very careful about linkage as we're doing this. All right, our trig functions, this is just a standard sine function with a transformation, horizontal shrink by 1/2. Domain is all real numbers. Over here, you only have to worry about the division by 0, so theta cannot be 0. Your log functions, when we take a look at those, your log functions, your input must be greater than 0. Remember, log functions have that vertical asymptote at the edge of their domain. And so I just simply did an input greater than 0, plugged it in, and solved this linear inequality. Fairly straightforward. If we take a look at the last one, you kind of have two things going on. In addition to having a denominator that can't be 0, you also have the square root that's in there. So I did both the denominator not equal to 0 and the radicand greater than or equal to 0. And then once I got these two values, x can't be -1 and x must be greater than or equal to -2. And then I combined these together, and notice I used in all of these, you're going to be using appropriate set or interval notation. They accept both, but it has to be a correct set or interval notation when we look at it. And then I just repeated the same thing over here for this one. So now when I'm looking at this, the idea is the second part of this, I'm going to change colors to green, says find each of the following limits analytically. Now the only method that you have right now is this direct substitution. So when I look at it, could I use direct substitution in A? The answer is yes. We can simply evaluate this limit, and the direct substitution is evaluating the limit. So I'm actually performing the limit when I do this direct substitution. So I don't have to write it. I simply plug in and calculate half of 3 squared minus 2 times 3 plus 3, and then I get my answer to that. So what is that? 9 halves minus 6 plus 3 would be minus 3. And we can leave it like that. Exact answers are fine in terms of finding it. We don't have to get it combined into a single fraction or anything like that. We have our answer at that point. If you wanted to do it by decimal, 9 divided by 2 is 4.5, minus 3 would be 1.5 if you wanted an exact decimal answer for that. All right, looking up here, in the B, we do have a discontinuity, and the discontinuity is at 3 halves. But I'm trying to calculate the limit as x goes to 3. And 3 is a location where there is not a discontinuity. Rational functions are continuous on their domain. So performing direct substitution for this value of A is perfectly fine. We simply do our plug and chug. And remember, we don't have to actually write the limit. We're performing the limit by doing the substitution. So 5 times 3 plus 2. 2 times 3 minus 3 is going to give us 15 plus 2, 17 over 6 minus 3 is 3, so 17/3, and we're done with that problem. Now we have a slight problem over here in this one that we're looking at. So notice that the value that I'm going in, this -3, is a problem. That when I go to plug in -3, I'm going to have a division by 0 problem. And we know rational functions are not continuous on our domain. So what this is going to tell me, this does not tell me the limit does not exist. Okay, that's the first thing that you have to recognize. Right now, if I know that I have a discontinuity there, the limit may or may not exist. What I'm looking for here is I can't use direct substitution. Cannot use direct sub. We're going to have to do something else. So we're going to come back to this in the next little portion or the next part of the video, because it's not that the limit doesn't exist. The limit may exist. We just need to investigate it further. And so that's kind of what we're going to look at in the next part. Now in this one, in sine of 2 theta, it was continuous everywhere. So clearly we can do our direct substitution. Notice I do not write the limit. That's weird. Why did it start out as red and then turn to green? Green equals sine 2 times pi over 2. That's the sine of pi. And then we evaluate our trig function. So you do need to have a little bit of knowledge of trig. Sine is the y-coordinate on the unit circle. And the y-coordinate for an angle of pi is going to be like, if you think about your unit circle, pi goes to there. Your point is going to be -1, 0. The y-coordinate is 0, so the sine of pi is 0. So we can evaluate that limit. In this one, we have the limit as theta goes to 2 pi over 3, and our problem was at 0. So we don't have a problem. We can direct substitute on this one. Again, we're performing the limit. So we simply do the direct substitution. 2 pi over 3 over 2 pi over 3. Now a little reminder of trig for that one. So 2 pi over 3, if you will remember, is going to be in quadrant 2. It's located there. The coordinates for the pi over 3 family would be negative 1/2 square root of 3 over 2. Cosine is the x coordinate. So we want the x coordinate, which is negative 1/2 over 2 pi over 3. And if we wanted to simplify because of the fractions, we could flip and multiply, and it becomes negative 3 over 4 pi. And that would be our final answer for that one. All right, we can look at our log here. 9 is in the domain, and log functions are continuous on their domains. So we can use direct substitution. So we're going to do the log base 8. And again, I'm only not writing the limit because by direct substituting, I am actually taking the limit. 11 minus 9 is going to be 2. In my head, doing arithmetic. And now, we have to remember how to evaluate logs. So remember that when we're doing logs, what we're basically doing for that, and I'm just going to scooch this over to this side right here so that that's out of the way. We'll make it a little tinier so that it doesn't bother me. So this log over here, remember that when you are evaluating logs, so we're doing a lot of nice review while we're looking at this, that the log base 8 of 2 is saying what exponent, okay, what exponent do you raise 8 to? So 8 to what exponent is going to give me 2? And so now, of course, we're going from a big base to a smaller number. So you might recall that that's going to have to be a root of some sort. And if you think about what root, 2 is actually the cube root of 8. And what power represents a cube root? That would be to the 1/3 equals 2. So log base 8 of 2 is 1/3. So a little log review in our little activity here. All right, now over here on this one, we're approaching 2 from the left. And when you look down here, 2 is in the domain. So if 2 is in the domain of this radical in a fraction, then it's continuous on its domain. A lot of our basic functions that we learned in pre-calculus are continuous on their domains. So we know that we can direct substitute. So in this one, we would end up with, and the 2 from the left actually doesn't matter because remember, we'll put a little star by that and I'll come out here. Maybe I'll change colors to something brighter. Let's do hot pink. So over here, when you're doing the limit as x approaches 2 to the left of a function, where we know f of x is continuous. Now, the idea here is that it doesn't really matter that it's from the left, because when we're looking at it, we know that continuous functions are connected and the function value is exactly the same. So the limit as x approaches 2 from the left of the function is going to be exactly the same as the limit as x approaches 2 from the right of the function. And that's going to be exactly the same as f of 2, that it doesn't really matter because it's a continuous function. So we can basically plug the 2 in just like we're doing direct substitution. Again, you don't write the limit anymore because we are taking the limit right now. Square root of 2 plus 2 is 4. Minus 1 over 2 plus 1, 3. So 2 minus 1, 1/3 would be our limit for that one. All right, and then our final example here, as we approach 1, 1 is a problem because you can see here in our domain that we were calculating, we have a division by 0 problem with that. That doesn't mean that this is a D&E, okay? Again, coming back in, this does not mean that we can't do it or that there isn't a limit. The limit may exist, but we cannot use direct substitution. So cannot use direct substitution. So we're going to need a different strategy for that one, and that will come later in these notes. All right, so I'm going to stop this video at this point because this is a short enough video to say, what do you do when you have a continuous function? The whole main point of what I've done up to this point is if the function is continuous, you can evaluate the limit and find the limit by simply plugging the a value into your function and getting the function value. Because for continuous functions, the limit and the function value are exactly the same.